Hello, this is Nick of Time. Welcome to this, the 14th talk on the physics of time. Recently, we've been talking about the empirical data for clock slowing, clock retardation, time dilation, and how it compares with special relativity's time dilation equation. I want to make a quick point, but an important point before we get into the main topic of this talk. When we've been examining data from clocks, we're talking about very fundamental clocks that work by fundamental atomic processes going over and over at a regular rate. For example, for the GPS, Global Positioning System data, we looked at atomic clock rates. And there we were looking at, and I just modified the definition of the standard definition for a second. So we're looking at the duration of periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. So if that doesn't mean a lot to you, you can still get the idea that we're talking about a fundamental process rate for atoms. Similarly, for particle accelerators, we were also measuring a fundamental particle process, and particle would be something like a muon. A process rate, namely the half-life decay of some of these particles that are created during a collision. So we're not necessarily talking about mechanical clocks with a pendulum or a spring. These are fundamental atomic processes, and that will be the case for the next set of empirical data. Also, I'm going to continue to talk about muon half-life decay. But in this case, looking at the picture, we have a cosmic ray coming in from the upper left. And when it gets to the top of the atmosphere of the Earth, it can strike a proton or a neutron and create a shower of secondary particles, including muons. And it's noted that from these collisions, the muons travel through the Earth's atmosphere, and many, many of them strike the Earth's surface. But this creates a problem. We're going to look at that problem. This creates a problem for special relativity's time dilation, because muons have a short half-life before they disintegrate or decay. But there's a long trip through the atmosphere, so it would take a long time in the terms of a half-life. So only 1 in every 10 to the 138th, which is a humongous number, are expected to survive. Yet, many, many of these atmospheric muons hit the Earth's surface. Now, their half-life when they're at rest is only 2.2 microseconds. But the time to travel through our thick atmosphere, even at the speed of light, would be 700 microseconds. So how do they get to the surface of the Earth? The only way to explain this is that their half-life might be expanded because their clock rate must slow. And initially, this was just accepted as more proof for special relativity. But if you do some critical thinking, you say, well, as we've done before, and which we'll repeat now, since special relativity, time dilation, is a function of relative velocity, that must mean it's symmetric between the two clocks that are traveling at a relative velocity one to the other. And if you say that time dilation is describing physical slowing of clocks, that's equivalent to saying A's clock is slower than B's clock, and B's clock is slower than A's clock. Did I say that right? A's clock is slower than B's clock, and B's clock is slower than A's clock, which is an obvious contradiction. We'll continue to look at this. What did the relativists say to that? Well, they tried to explain it as follows. They invoke relative simultaneity, which in turn invokes a just observed interpretation. So they claim a muon at rest would have a long life in the fast atmospheric muons frame. So they're saying, well, it's just an observed effect. But just from common sense, we kind of sense that the muon clock must have physically slowed to be able to traverse the atmosphere when it was only expected to live for 2.2 microseconds, and the time to travel even at the fastest speed would be 700 microseconds. So we'll look into that a little bit more. So the explanation that we talked about was one that was used to explain the alleged time dilation data from particle accelerators. But here we have a different problem. It's a threshold problem. There are two thresholds, or two absolutes, and that causes a problem for that special relativity rebuttal. The first absolute or threshold is the muon either hits the surface or it doesn't hit the surface. And in this case, we have many, many hitting the surface when they shouldn't be hitting the surface. Number two is that special relativity says that speed of light is the maximum speed limit. And that's a fact. I'm not claiming that the speed of light is the maximum speed limit is the fact. It's a fact that special relativity says that's a fact. So, the only way for the muon to hit the surface of the Earth without their clock physically slowing in the Earth frame is to go faster than the speed of light in the Earth frame by a factor of 300. And that would violate special relativity. So those two absolute facts that we talked about bound the problem and bound any rebuttals so that special relativity has to be violated by one or the other. Either the muon's clock has to physically slow, which special relativity's time dilation can't explain, or the speed of light has to be, as a speed limit, has to be violated, which would also violate special relativity. So this set of data is the second set of data, along with the GPS data, that shows that special relativity's time dilation cannot explain this phenomenon of actual physical clock slowing as a function of velocity. So, looking at the data from muons that were created in the upper atmosphere and hit the Earth. Now, I've been, to make the exposition simple, I've been talking about a single muon, but the basic logic applies if you look statistically at a whole set of muons. There can't be that many that hit the surface of the Earth without having the problem that we just talked about on the previous slides. On the one hand, like data from particle accelerators, we don't have data from the muons perspective, but because of this special situation with two absolutes constraining any rebuttal, we see that atmospheric muon clocks must have physically asymmetrically slowed. So this effect cannot be explained by special relativity's time dilation, which is inherently symmetric and just observed and not causing physical effects. So, once again, thank you very much for joining us as we look at this interesting topic. And we have one more source of time dilation, clock slowing data that we'll look at next time, and then we'll go on to even more topics. So thanks for joining us. Hope to see you next time.